LeetCode problem 2. Add two numbers. Isn't just a warm-up. It's a glimpse into real systems, like financial pipelines or telemetry feeds, where digits stream in and overflow is a real threat. We're dealing with reverse-ordered digits, and we need to compute the sum without ever converting to full integers. Sounds basic, but the deeper challenge is scalability. Let's kick things off with a brute force approach. We'll convert both linked lists into full numbers, add them, and then build the result list from the sum. Feels duck soup simple, right? We'll set up two variables to hold the numeric values from each list, plus a multiplier to track digit placement as we extract digits one by one. While walking through the first list, we compute its numeric value by multiplying each digit with the current place value, then scale the multiplier by 10 for the next digit. After converting the first list, we reset the multiplier and repeat the same extraction process for the second list, building its full number step by step. Now that both numbers are fully constructed, we can go ahead and add them together directly. But before we build the result, we check for the edge case. If the sum is 0, we just return a single node list with value 0. To assemble the result, we introduce a dummy node to act as a placeholder. It helps cleanly manage edge cases as we build out the new list. As long as there are digits left in the sum, we grab the last digit using modulo, drop it into a new node, move the pointer, and trim the sum down using integer division, rebuilding the number in reverse order. When we're done, the result is the next node after the dummy. That's our actual output list. This brute force version runs in big O of n plus m time, around 200 operations for 100-digit lists, and uses similar space. But here's the red flag. Converting to integers can cause overflow. Java's int maxes out at 10 digits and long at 19. So this method won't scale. It's efficient for small cases, but risky for real data. Time to level up. Let's skip full number conversion and instead add digits one by one, just like we do by hand. This avoids overflow and handles long lists gracefully. Here's how we improve it. First, we drop in a dummy node to anchor the result list and set up a pointer to track our current spot as we build. We also set up a carry variable to track overflow from summing digits that total 10 or more, starting at 0. Here's our main loop. We keep going while either list has digits left or if there's still a carry. This covers uneven lengths and final overflow digits. Each round starts by setting our sum to the current carry from the previous step. If the first list still has digits, we add that digit to the sum and move to the next node. Same drill with the second list. If it has digits left, we add the value and move ahead. Once we've added both digits and the carry, we update the carry. It becomes 1 if the sum is 10 or more, otherwise it resets to 0. We then create a new node with the ones place of the sum, that's sum mod 10, and attach it to our result list. Next, we slide our result pointer forward to prep for the next digit we'll add. After the loop wraps, the list starts right after the dummy node. That's our final result. This method also runs in big O of max of n and m time, with the same space for the result list. But here's the win: no overflow risk. We only handle one digit and one carry at a time. It's clean, safe, and scales perfectly, the kind of approach interviewers love. So we began with a brute force method, clear and easy, but limited by potential overflow, especially in Java. Then we shifted to digit-by-digit addition, handling carry and structure manually. That gave us safety, flexibility, and real-world readiness. It's the kind of technique that shows up in FAANG interviews and in scalable back-end code. So here's your challenge. Where else can this pattern shine? Think streaming digits, compressed formats, or memory-bound systems. Stay curious, stay clever, and keep quacking forward.